Have you seen the test?
I have not seen the test. But I've seen the practice tests, and I've seen other tests from Dr. Franson, and they are all very similar. So, in a way, I have seen the test. All right. Well, let's talk about econometrics, okay? Let's go from the beginning of the class. Let's go to the end of the class. It's actually not going to take very long, despite all the hours that you've spent in lectures. So, econometrics uses data to answer causal questions. Okay? So, let's start with a question. Okay? I'm just going to put Q because I don't want to write the word question here, but you can just imagine that says question. And there are different types of questions. There's causal questions, and there's predictive questions, right? So if I were to say, what is the relationship between shark attacks and ice cream consumption, right? That would be what kind of a question? Causal correlation, which one? Correlation, I would agree. Okay. What if I said, what is the effect of eating ice cream on getting attacked by a shark? That sounds like a causal question, right? Those talk about the exact same relationship, but the question is different. And in econometrics, we want to isolate causality. That's what we're all about here. So let's say that we're in some universe, and let's say in this universe that we're in, that we've got our world, and we've got the world of demons, right? And demons, they want to come in and attack us. The only way to stop from getting attacked by demons is through the power of music. And so we have all these pop stars. Let's say they're K-pop stars. And they have a dual job of singing K-pop hits to bring people together and fighting demons, on the side. Okay. So there's just a bunch of these people. All right. K-pop's a big industry. All right. So let's say one of these K-pop stars, her name's Zoe. Zoe says, "Hey, I really think that the more makeup that I wear, the more I spend on makeup, the more demons I kill. I just feel like this is something this is an actual relationship, right?" So Zoe is asking what type of a question? Causal. That's a causal question, right? The question is, does spending more on makeup help me kill more demons, right? Okay. That's a fair question from Zoe. So Zoe's got a question, okay? And to model this question, she's going to use some type of model. Let's say she uses a bivariate linear regression. So let's say regression looks like something like this, right? She says yi equals beta naught plus beta 1 x 1I plus epsilon I. Use that to model her question. So here, what would yi represent? Yeah, how many demons are killed, right? Beta naught to intercept. x1I is. Okay.
She spends on makeup.
X1I. X1I is makeup spending. And how much do I spend on makeup? Beta 1 is the effect of spending makeup on killing demons. She thinks it's positive. And epsilon is everything else that affects killing demons. All right. So cool. So something to think about, and this is what econometrics, a lot of econometrics is about. First of all, identifying what the heck this is. Secondly, being able to say, okay, so she thinks the sign is positive. What's the reason why the sign would be positive? Why would spending more on makeup help you kill more demons?
Confidence.
Confidence. All right, you're on point. You're confident. You feel better about killing demons. Nice.
Look good, sing good.
Look good, sing good. Right? Heels, nails, hair, mascara. Right? Kill more demons. So, what's an example that the sign might be opposite of what you would expect?
Makeup in her eyes.
Yeah. So much makeup that you can't kill demons. Right? That's okay. So you guys are so good at econometrics. You can do all of this already. All right. So she does this model, right? But in order to assess this model, she needs some data. All right. So she gets a data set. what would be an example of a cross-sectional data set for this question? Well, let's assume we're in a world with lots and lots of K-pop demon hunters in various different agencies around the world. What would a cross-sectional data set look like?
K-pop hunters.
Okay, perfect. You get a bunch of different K-pop demon hunters, and you have how many demons they kill, how much they spend on makeup. Okay, what would a time series data set look like?
Just following one over multiple time periods.
Okay, yeah, so you have just Zoe, right, in time period 1. How many demons does she kill? How much does she spend on makeup? What about a panel data set?
Combination of both.
Okay, you'd have a bunch of demons with that time, or demon hunters, sorry, with that time series going on. And you guys don't really talk about pooled cross-section, but pooled cross-section is just kind of like a panel, but you take cross-sections from different years, but they're different people. Like you don't keep the same people for every year. But you guys don't really talk about that, so there's not really any reason to know that for like an exam or something like that. Okay, so she's got her data, right? And now she's going to estimate it. And she's going to estimate her data with the only estimation method you guys actually know right now, which is OLS. Okay, so she's going to use ordinary least squares because she doesn't know two-stage least squares. She doesn't know maximum likelihood estimation. All right, none of that. So she's using OLS to estimate her data. She's going to take the sum of her squared residuals. She's going to derive those estimators, and she's going to get it done. And then she's going to do some inference. Okay, so I like to think of this as Kim Day, right? Like Kim Day. I imagine she's like this Asian economist girl that's really smart. So that's our limit. Okay, if that works for you, then great. Okay, but let's do some inference. Okay, so she gets her data, she gets some inference, so her X bar is 5. Okay, so the average makeup spending for one of these K-pop demon hunters is $5,000. Okay. All right, the Y bar, 12. 12 demons killed, okay? She got a variance of X, that ends up being 4, all right? And then the covariance of X and Y ends up being 3.2. All right, so now I might ask you a question like, what is beta hat 1, okay? And how would you find that? What is the formula for beta hat 1?
Variance over X and Y.
Oh, it's the covariance of X and Y over the variance of X, which would give us 3.2 over 4. 0.8 is your beta hat 1. Okay, and what about beta hat 9? What's that one?
Minus beta hat 1 X bar.
Perfect. That is exactly what it is. So you take your Y bar of 12 minus beta hat 1, which is 0.8, times X bar, which is 5, gives you 8. Perfect. So just like that, you have your estimators. Beta hat 1, beta hat 9. Perfect. Okay. What if you wanted the variance of beta hat 1? Variance of beta hat 1. This is a bit of a, I'll just write this one out, actually. Okay? So this is sigma hat squared of your epsilon, right? And that's over, I'm gonna call this SXX. And what I mean by SXX is just the sum of all your squared deviations from the mean of X. Okay? So there's your formula for the variance of beta hat 1. And let's say that, we also need to know what sigma hat squared epsilon is, right? So this right here, the equation for this bad boy is the sum of the squared residuals over n minus k plus 1. And k here is the number of regressors you have, but in the bivariate case, you just have one regressor, so that would just be n minus 2. Yeah?
Is it okay if you can write just a little bit bigger? Hard to see.
Oh, yeah. Do I need to rewrite anything, or just from now on?
Just from now.
Okay, sorry. This?
Yeah, what is that?
This is a sigma hat squared. This is the variance of your residuals, or the observed variance of your residuals, rather. Okay?
What is SXX? Like, what does that mean? Like, is there a vocabulary or something for that? SXX?
Really, I just don't want to write this out. But I mean, if you had like the sample variance of x, you know, the sample variance of x is going to be 1 over n minus 1 times that, right?
So it's like SXR.
So no, it's just a term. Like I'm just gonna call I'm just gonna call this SXX, so I don't have to write that whole thing out. But it's just the sum of the squared deviations from x bar. Yeah. So it just helps me write this formula really simply and remember it, because that formula is kind of hard to remember for me. So yeah. So let's say we get that this is 7, this is 116, and therefore variance of beta hat 1 is 7 over 116. Therefore our standard error of beta hat 1 is going to be root 7 over 116, which is about 0.25. Okay? So there you go. That's how you would find the standard error of beta hat 1 in such a case. I'm still not writing big enough, huh?
Just a little bit more.
Okay, I can increase the size of writing. Sorry. Okay. So now we have everything we need to perform inference. Let's do a t-test on this. Okay. So a t-test is the well, here's our beta hat 1 minus. Oh, I'm so sorry. I forgot our ingredients for a t-test. My bad. You need a null hypothesis. You need an alternative hypothesis. You need your stat, which is t-stat, and you need the distribution of your t-stat, which in this case, under our assumptions, is going to be normally distributed. 0. Whoa. I forgot how to write the notation for this. But basically, does your variance go first? No, your mean goes first.
0, 1, yeah. Yeah,
0, 1. If it,
It's actually 0, 1?
Yeah.
Oh, okay. Well, there you go. Okay, so we're going to perform some inference here. So let's say our null hypothesis, right? Makeup spending has no effect on how many demons we kill. All right? So therefore, beta 1 equals 0. Okay? All right, null hypothesis, beta 1 does not equal 0. Easy enough. We're going to perform a t-test. We're going to have our standard, our t-stat is going to be beta hat 1 minus 0, that's our hypothesis, over the standard error of beta hat 1. Okay, that's how you perform any t-test or z-test for literally anything ever. So, beta hat 1 minus 0, of course, where's our beta hat 1? 0.8. 0.8 over our standard error of 0.25 gives us, I don't know, we have that. I think it's like, say 3.2? 3.2? Is that right? Okay, let's say it's 3.2, right? So then our confidence interval would be our observed value, beta hat 1, which is 0.8, plus or minus, let's just use 2 as an easy number, standard errors, right? That's how you make a confidence interval. So we got 0.8 plus or minus 2 times our standard error of 0.25. Gosh, 0.25. And that gives us a confidence interval from 0.3 about to 1.3, somewhere around there. And that is how you do a confidence interval. It's a little 378 review for you guys. So cool. We know how to do inference with our stats. Any questions on any of the Kim Day process so far? All right.
Sorry, will you explain when you're solving for the t statistic, beta 1 hat minus 0 over standard error?
Beta 1 hat we calculated right here. Standard error for beta hat 1 we calculated. Did I even write that down?
Yeah, you did.
Right there.
Right in the middle of the board.
Oh, this one?
Yes, that.
Well, yeah. Yeah. Yes. Oh, okay. Sorry. So this is the variance of beta hat 1, right? And then the standard error is just the root of the variance of beta hat 1. Does that answer your question?
I guess my question is more what equation are you plugging those into to find t? Like what's the equation that you're looking at there?
This equation?
Yeah.
Just any time you do really any test at all, z-test, t-test, you're doing kind of this, you remember doing z-tests in 378 where you had x minus mu over sigma. Does that kind of look familiar?
Yeah.
So basically you have your observed value minus your hypothesis over your standard deviation.
Okay.
Which in this case is, our observed value of beta hat 1 minus our hypothesis for what beta hat 1 is over our standard error of beta hat 1. Yeah.
Are you recording?
I am.
Sweet, okay.
So 16 minutes and still counting. Cool. Okay, so this is what we get. Okay, and we get a t. What was our t? 3.2. So what do you say? Is that significant?
Yes.
Yes. Right. That's pretty darn significant, right? Because what's the number we're comparing that to? 2. Yeah. Pretty easy. We're not getting super into the 378 stuff. So we have determined that spending money on makeup actually helps you kill more demons. Okay. Are there any problems with this?
There's a lot of things like
Okay.
Like, what is the intuition so you can go in order and like figure everything out, like have a good flow? You know what I'm saying?
In terms of, I
In
guess
terms of
we're
like finding everything out, because there's tons of formulas. Like, should we do you recommend for us to like, I don't know, memorize certain things or like a process so we can go from 0 to 100 and get everything right?
So I would say what should come, I mean, all of these things will be asked in separate questions. Like, you don't need to go through this whole process, like, from memory. But things you should definitely know, like this should be really natural. What the formula for beta hat 1 is and what the formula for beta hat 0 is. You should know those off the top of your head. If you're given a bunch of numbers, then you should be able to calculate the standard error of beta hat 1, and you should be able to run a t-test. So know these formulas. These are very important. This one's a little trickier. I would put some work into memorizing this right here. Which also involves knowing the SSR over n minus k plus 1 for your sum of squared residuals. And then you should be able to run a t-test with that as well. Does that answer your question? Yeah. Yes.
For the sum of square residuals, is it just like the unrestricted, or does that matter in this case?
We're just doing bivariate right now. So it's just there's no restricted, unrestricted. It's just literally just your residuals for your one regressor.
How important is it that we know the derivation of the b hat 1 being c covariance?
The derivation?
Yeah.
Very important. I would place that very high on the importance. Yeah.
Okay.
Yes. Sometimes, he said in class, like sometimes he puts like communicate findings right here. I haven't seen him do that on a test. He might. I don't know. Okay, so problems, right? Why might this not be the true causal effect? Yes, Lexi.
Maybe it's actually like your outfit and just people who like buy better clothes buy more makeup. Like
Okay.
maybe there's an omitted variable.
So, omitted variable. So let's say clothes, right? Your outfit helps you kill demons, is that what you're saying?
Yeah, like a good killer outfit.
A killer outfit, okay. So a killer outfit helps you kill demons. Okay. What I just said, is that enough to call it an omitted variable? No, why?
Has to be correlated with xi. That's
Yes. Oh my gosh, you just raised the average score of this class by a full point. An omitted variable is correlated with y and x. Okay? It's not just something that is in your epsilon that affects y. That's part of it, but it's omitted because it affects y and x, both of them. Okay? So, if it were true that, okay, the outfit that you wear, that helps you kill more demons, and it's actually correlated with how much makeup you wear, which, that's reasonable, right? So that could be an omitted variable that we have to include. We could control for the outfit that you wear. Okay, perfect. What is another possibility besides omitted variable bias that could make this regression not good? Yeah.
Like a violation of homoskedasticity, like the variance is different at different levels of x, or the variance of the error term.
Okay, so what would homoskedasticity, or I guess, what would heteroskedasticity do to our estimators?
So the error would be unevenly varied across the distribution.
Mm-hmm. And the consequence, does it make them biased? No, it doesn't make them biased. Does it make them inconsistent? I don't think it does. I'm sure I could be wrong on them, but I don't think it makes it inconsistent either. What it does is it throws off your standard errors. And because it messes up your standard errors, it's going to make inference really difficult. Okay? So heteroskedasticity messes up your standard errors, and therefore that's how it messes up your inference. But it doesn't make it biased. The only thing that makes it biased is a violation of exogeneity. Okay? Okay, perfect. The other thing we've talked about besides omitted variable bias that would be a violation of exogeneity is what? Does anyone know? All right, I'll just tell you. It's reverse causality. Okay, does that sound familiar? Okay. So what would reverse causality be in this situation?
Killing demons makes you buy more makeup.
Yeah, you kill more demons. Maybe you feel better about yourself, so you spend more on makeup, right? Or maybe you get a commission from killing demons, and then you spend more on makeup. Either way, so that would be reverse causality, and that would be a problem. Now, just so you know, okay, so we're going to fix omitted variable bias. We're going to assume the problem is omitted variable bias, which we would solve by including the variable, right? Would that fix reverse causality? No. It would not, because reverse causality is a different problem where x depends on y, which you can't fix by just adding more variables to regression. Okay? So we're going to assume the problem is just omitted variable bias for this case. Now, yeah, just something else to add there is that zero conditional mean assumption is most likely to be violated when people can self-select into x, right? So if people can self-select, if they have control over how much they spend on makeup, which they do, then that is a pretty huge problem. So it would not be a problem if we ran a randomized control trial and we just gave a bunch of different people different makeup budgets and said, this is exactly how much you have to spend on makeup, and then we observed how many demons they killed. If it was completely random, then that would not be an issue. But it's not, because they're self-selecting into X. Okay. Yeah? Okay. Cool. So let's fix it. Let's talk about some reasons to run. Let's get all these equations off the board. Yuck. Okay, reasons that we might do a multiple regression. Okay? Okay, reason number one, we just talked about it. Eliminate OVB. Okay, we want to get rid of that omitted variable bias. Reason number 2, we care about more than one variable. Okay, so we actually want to know the effect of your outfit on how many demons you kill. So that's why we're going to include it, all right? Number 3, to allow nonlinear functional forms. Okay, so we can have a x1 and x1 squared in there, and x1 cubed. So we believe the relationship is nonlinear. Okay, and it also improves the precision of our estimates. Okay, so the more variables we include in our regression, the higher our R squared goes, and the smaller our standard errors are. Okay, so the smaller standard errors, then your inference is technically more likely to be significant. Okay, because you have more variables explaining them. Yes.
So is functional form a different type of estimator, or is it still multiple variable? Analysis.
Still multiple regression?
Yeah.
Is that what you're saying? It's still multiple regression. Like, you know, to explain this, like I might write it like this. I might say beta 2x squared plus beta 3x cubed plus epsilon. Yeah. But that's really just for like educational purposes, right? Like functionally in Stata, what this looks like is just x1i, x2i, x3i. Those are all just different variables with different values. Does that make sense? Okay. All right. So we go into multiple regression, and let's write that bad boy in matrix form over here. So multiple regression in matrix form looks like y equals x transpose beta plus epsilon. Okay, perfect. So our y matrix right here is just going to look like a big vector of y variables. 1, 2, all the way to yn. Our, correct me if I'm wrong, right. Our X matrix.
Our ledger stray is not transposed.
Yeah. Is it? I thought I read
It is transposed.
It is?
It is, okay. Good. Okay, our X matrix is going to be, so this Y matrix is going to be n/1. Our X matrix is going to be our, well, it's going to have a bunch of ones right here. It's going to have X1, 1. Oh, shoot.
It isn't transposed.
So it's
Because
So
in matrix form.
in matrix form, but in vector form it is.
Oh, why did I have a transpose there?
Because in vector form it is.
So it is.
Oh, okay.
Supposed to be.
Good.
Wait,
So
but he's drawing it in matrix form.
The top thing is the
Let's just observe the matrices and let's find out. We'll find out. Okay. I always get confused. So x1 1. So this would be x2 1. Yeah. I feel like that's right. All right. All the way down to xn 1. Whoa. And this would go all the way. You've got an x2 1. Oh no x1 2. x2 2 all the way to xn 2 goes to and this goes k times, right? So this is x 1k x 2k all the way down to x n k. Yeah. So this matrix is going to be n by k plus 1. Okay. So you got an n by k plus 1 for your x, and then your beta is going to be some matrix of your, beta naught, beta 1, beta k. Oh, and epsilon. Right, you got your epsilon 1, epsilon 2, epsilon n. Okay, well, let's figure out if we did this right. So your y is going to be an n by 1. Okay, n by 1. And you have x beta, well, that would give you an n by k plus 1 times a k plus 1 by 1. okay, which leaves you with an n by 1. And then plus epsilon, which is an n by 1. Okay, all right, that checks out. So it's not transposed. You guys were correct. At least some of us. Okay, perfect. So that is how you would write your regression in matrix form. There's also a way to write it in like semi-matrix, like vector form. You guys can do that too. I'm not going to do that. Yeah.
Just to make sure I got it right, dx, the reason it's a matrix, those are each observations. Like, the ones are all with beta naught, right? And then,
Yes.
and those are all each observation, like each observation that would be tied to beta 1, beta 2, beta 3.
Yeah, yeah. So if I were to multiply this bad boy, I would take this row, and it would get flipped up. It'd go right along this, right? So you get your beta naught plus beta 1 x11 plus beta 2 x12 all the way to beta k x1k, and then you do that for all of these lines.
And that would just give me, as soon as I added epsilon 1, that would give me y1, in a sense, right?
Yep.
Okay. I'm chilling now.
Your first observation. Yes.
Is it important to like know like ordering n and k the right way? Because I like in my head I kind of get them mixed up all the time. If I have to write out the matrix, is it important that I know which one's n, which one's k, or like which order they're written in the subscript?
If you don't, I would just define them well. So whatever you're doing, like this should be observations. Right? This looks just, your X matrix looks like just like a data set in Stata. So this is how many observations you have, and this is how many regressors you have. Okay. Cool. Okay, so that is our multiple variable. Our multiple regression, not multivariate regression. That's a completely different thing. Not a completely different thing, but it's not the same thing. Okay, so what else should we talk about? This is my least favorite thing to talk about, but let's talk about f-stats, I guess. So if you were going to run some kind of f-test, this is another formula that you should probably memorize, even though it's kind of rough. You have your SSR restricted minus SSR unrestricted over Q over your SSR unrestricted times n minus. Okay, so that is how you would get an f-stat, where Q is the number of hypotheses you're testing, or the number of regressors you're testing hypotheses on. Okay, and then K, of course, is your number of regressors total in your regression.
Which SSR is on the bottom of that?
This is unrestricted. Unrestricted. Yep. So here's your f-stat. If you're running an f-test, it's for multiple variables. You could run an f-test on a few, or you could run an f-test on the whole thing. And if you're plugging your stuff in this data, it'll run the standard f-test, which is that beta naught equals beta naught, right? Beta naught equals beta 2, blah, 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 equals 0. I don't know if it includes beta naught. Does it not? Yeah, well, it'll run this and tell you if they're jointly significant data. Okay, and that'll depend on your f-stat, which is going to be f distributed with k degrees of freedom for your numerator and n minus k minus 1 degrees of freedom for the denominator. Yes. That is what we get for the f-test. Yes?
How do we calculate SSR and SSU?
Those would be given to you.
Okay.
Yeah, in the example, in the sample midterm that he gave, he actually just said, how would you run an f-test on this? And he probably this test is gone, but you just really gave the ingredients, right? You gave the H null, you gave H1, and then you gave what the f-stat is. So he had you provide this, and then he had you say the distribution. Let me make sure that's right, because. Yep, yeah, that's right.
Could you walk us through what that would look like in a problem? Like maybe examples of each of those?
Like an F-stat?
The things that you just mentioned, so like the null hypothesis, the degrees of freedom, I think you said, like the things that he would potentially ask for, just like what each one of those might look like.
Yeah, so let's say you wanted to test, does beta 1 equals 0 and beta 2 equals 0? Let's just say that's what we want to use this. Okay, this is a joint significance test. So you do an F-stat. We're testing two hypotheses, right? So your Q here would be 2. N is going to be your sample size for the whole data set. And then K is the total number of regressors you have. So let's say, let's say in this case you have 3 regressors, right? So your K is going to be 3, but your Q is going to be 2 since you're testing 2 hypotheses. Okay, so Q is 2, K is 3, and then again I didn't even write that. SSR restricted, that should have an R by it. SSR unrestricted over Q. Yeah, and so you would plug those bad boys in, you get an F-stat, and it would tell you whether these are jointly significant. I don't think he's going to have you run an actual F-test, because I don't think he's even told you like what number to compare to for the F-test. I think off the top of my head it's like 10 or so. I don't think he's ever mentioned that. So.
What is Q again?
Q is the number of hypotheses you're testing. 2 in this case.
So he mentioned that you could use, you'd use a t-test and you can test multiple slopes at the same time, but it's just one hypothesis versus this multiple hypothesis test. What does that exactly mean?
If you're testing multiple slopes at the same time, that sounds like multiple hypotheses to me because it's how many equal sign you have, right? So even if you said my hypothesis is beta 1 equals beta 2 equals beta 3 equals 0, that would still be testing 3 hypotheses, yeah?
I think it's when he was testing beta 1 minus beta 2 equals 0.
Oh, like a difference test. Yeah, if you were doing a difference test, beta 1 minus beta 2 equals 0.
It's just one hypothesis still.
And that's that single hypothesis.
Yeah, this is the same as beta 1 equals beta 2. Yeah. Good catch. All right, let's stop talking about that. I hate talking about F-tests. Cool. So let's go over, man, we're almost done. Let's go over the Gauss-Markov assumptions. All right, so I'll give you the book version and I'll give you the Franson version. Okay? So here are the Gauss-Markov assumptions from the book. I'm just going to write this in one line, right? You're assuming that your data represents a linear, full rank, random sample. I'm running out of space. With a 0 conditional mean, and I never use this right hand sign, but I'm using Homokedasticity. That is what your book says. Okay? As your data represents, under the Gauss-Markov assumptions, a linear, full rank, random sample with 0 conditional mean and homoskedasticity. There are 5 assumptions there. Dr. Franson put it into 4 assumptions. Mainly because he kind of ignores the assumption that it's linear a little bit, or accepts it as given, right? So his A0 is that X transpose X inverse exists, which is the same thing as full rank, okay? That's what that's saying. In the book doesn't use the term full rank, but it uses no perfect collinearity. Same thing. It means that your data is linearly independent, right? You don't have a dummy for male and a dummy for female, in the same data set. Okay, that would cause linear dependence, and therefore perfect collinearity. Same thing. All those are the same thing, okay? Then he says his A1 is the zero conditional mean, which is that your expected epsilon given x is going to be 0. Okay? I guess I'll write some minus there. All right. Then he has homoskedasticity, which I guess I'll put that mathematically. The variance of your epsilon i's given x is the same. I'll write this as several steps, but technically you don't have to write it as several steps. Just some, constant sigma squared on your epsilons. Okay, and then finally so assumption 3 he calls no serial correlation, which is that the covariance of your epsilon I and epsilon j is going to be 0. Obviously when I doesn't equal j, right? Because that would be the same thing. All right, so just for your information, that you don't really have to know this, but he calls this. Let me equate these. Right here, you got your zero conditional mean. Here you got your random sampling, and here you got your homoskedasticity. Okay, so really those are all the same thing. So basically what I'm saying is don't make one of your assumptions linear, even though that is one of the Gauss-Markov assumptions, because Dr. Franson does not recognize it as its own thing. Okay. So basically, for your FYI, no serial correlation is a terminology that matters in time series, and you guys are going to go into time series more in depth after the midterm. But it means that your epsilon for one time period is not correlated with your epsilon for the next time period, right? There's no relation between your error terms as you advance in time. If you were to apply this to a cross-sectional data set, though, essentially you're just saying that any two observations don't have correlations between their respective epsilons, which is basically just like saying that you have a random sample. Okay, cool. So that's your Gauss-Markov in book form and Franson form. But each of them, those are the 4 assumptions, essentially. And you should know the mathematical terms and the intuitive descriptions in them. Yes?
Would, if we were asked to describe assumption 3 intuitively, could we say, well, this means that, it's a random sample, or is that, would you say it means no serial correlation?
Yeah, either of those would be acceptable. Say both of them if you want to be super sure. Okay, so
In the proofs, that use vectors or matrix, do we have to identify the A naught assumption?
yeah. For example, if you were doing the unbiased proof, matrix form, is it the unbiased proof? Yeah, because this is in the definition of what beta hat is. So you would start by saying, hey, under assumption A0, I can actually write this. And then you would use assumption A1, you got to applying this as well. Okay, cool. So under these assumptions, your OLS estimate is blue, right? Which means it's the best linear unbiased estimator. Best meaning it is the lowest variance out of all linear unbiased estimators. If you get outside that category, then there are other estimators with lower variance. But out of all linear unbiased estimators, it has the lowest variance. Okay, linear meaning it's defined in linear terms, right? Unbiased